A corroded lump of bronze sat in a museum drawer for decades, hiding an impossible secret. This is the story of the Antikythera mechanism, an ancient Greek device considered the world's first analog computer. By the end of this video, you will understand how a single artifact rewrites everything we thought we knew about technological history. We will uncover how sponge divers stumbled upon a shattered masterpiece, why scholars initially dismissed its true purpose, and how modern science finally listened to the whispers from its intricate gears. What does a 2,000-year-old machine tell us about the peaks and valleys of human innovation? The year was 1901, and the Mediterranean Sea was not yet a highway for tourists. For a crew of Greek sponge divers, it was simply a workplace, a vast and often unforgiving expanse where they dove deep, holding their breath, to harvest a living from the seafloor. Their destination that spring was the channel between the islands of Crete and Antikythera, a stretch of water known for its strong currents and hidden dangers. They were looking for sponges, the soft, porous creatures that clung to submerged rocks. What they found instead was a ghost. As one diver descended through the dim blue light, his eyes adjusted to reveal a haunting scene. A human form, arm outstretched, seemed to emerge from the silt. It was a bronze statue, its features worn smooth by 2,000 years of salt and sand, lying amidst the broken columns and shadowy hull of an ancient shipwreck. The divers had accidentally discovered a Roman-era cargo vessel, a time capsule filled with priceless artworks being transported from Greece to Italy. The recovery operation that followed was monumental and perilous. Without modern scuba gear, divers risked their health in the deep, cold water, battling currents to bring up stunning marble sculptures, delicate glassware, and other bronze artifacts. Among this haul of obvious masterpieces was a far less impressive find. Pulled from the wreck was a corroded, lumpy object about the size of a large book. It was made of bronze, now green with age, and seemed to be fused with fragments of rotten wood. To the archaeologist sorting through the treasures in Athens, it looked like a shapeless mass, perhaps a piece of a statue that had melted together in the sea. It was catalogued vaguely and set aside, overshadowed by the more immediately stunning discoveries. For decades, this unassuming lump sat in storage at the National Archaeological Museum. Scholars who occasionally examined it guessed it might be a kind of astrolabe, a navigational tool used by sailors to measure the stars. This was a logical assumption, given it was found on a ship. But it was also a profound underestimation. The true nature of the object remained locked inside, invisible to the naked eye. Its secret would not begin to whisper until the 1950s, when a curious science historian named Derek de Solla Price took a much closer look. He saw not just a lump of metal, but a layered artifact, a mechanical puzzle waiting to be solved. This is the beautiful irony at the heart of the story. The most technologically sophisticated object from the ancient world was rescued from the deep, only to be mistaken for a piece of scrap. It was there, in plain sight, holding a mystery so advanced that the very people who found it lacked the framework to even recognize the question it was asking. The artifact's arrival in Athens marked the beginning of a long and puzzling conversation. In the museum's quiet study rooms, early 20th century researchers finally pried apart the wooden remains and peered inside the cracked bronze shell. What they saw was utterly confounding. Embedded within were intricate, toothed gears, some with precise triangular teeth, arranged in layered trains. Nothing like this had ever been found from the ancient world. The immediate instinct was to categorize it within known history. The most popular early theory declared it a navigational astrolabe, a reasonable guess for an object pulled from a shipwreck. But astrolabes are flat discs with sighting tools, not complex boxes full of interlocking gears. Other scholars, struck by the mechanical complexity, made a bolder leap. They proposed it was an astronomical clock. This idea, however, created a bigger problem than it solved. Everyone knew that geared clocks of such sophistication did not appear in Europe until the Middle Ages, over 1,000 years later. The very existence of this device seemed to violate the established timeline of human invention. So, the prevailing academic opinion settled on a convenient middle ground. It must be a later object, they argued, perhaps from the Renaissance or even the 18th century, that had somehow fallen into an older shipwreck. This was not a careless mistake. It was a failure of imagination, constrained by a deeply held belief about linear progress. The scholarly consensus of the time viewed history as a steady, upward climb. The ancient Greeks were philosophers and artists, brilliant in abstract thought, but not precision engineers capable of miniaturizing the cosmos into a bronze machine. To accept the Antikythera mechanism as genuine was to accept that a peak of technological artistry had been reached and then completely forgotten, leaving no trace in the historical record for centuries. This cognitive bias was so powerful that it rendered the object invisible as what it truly was. For nearly 5 decades, it remained a curious anomaly, a ghost in the museum's collection that whispered secrets no one was prepared to hear. The key to unlocking its story would not come from traditional archaeology, but from a new way of seeing, one that could look past the corrosion and listen to the silent mathematics etched in its metal bones. The mechanism's silence was finally broken not by a whisper but by a beam of invisible light. In the 1970s, a physicist named Derek de Solla Price, whose curiosity had never waned, teamed up with a radiographer named Charalambos Karakalos. They brought the corroded lump to a hospital in Athens, not for treatment but for revelation. Their tool was radiography, the same technology doctors used to see inside the human body without making a single cut. They placed the artifact before a source of gamma rays and X-rays, and for the first time in 2 millennia, light passed through its crust of green corrosion and ancient sea deposits. What developed on the photographic plates was nothing short of a mechanical ghost, a blueprint from the past. The images revealed not just 1 or 2 gears, but an entire cosmos in miniature. They mapped over 30 interlocking bronze gears, some with as many as 223 precisely cut triangular teeth, each smaller than a grain of rice. They saw nested dials, pointers, and a complex differential system, a kind of gear assembly that historians believed was invented in the 16th century for automobiles. This was not a simple astrolabe. It was a machine of breathtaking ambition. The awe those researchers must have felt is hard to overstate. They were staring at a level of mechanical sophistication that, according to every textbook, should not have existed for another 1,000 years. It was as if they had discovered a pocket watch in a Neolithic cave. The radiography did more than just count gears. It began to translate a lost language. Faint inscriptions, Greek letters etched onto the plates and covers, became visible through the crust. These were not random markings. They were labels, instructions, and a user manual fused to the machine itself. This non-invasive peek beneath the surface transformed the object from an archaeological curiosity into a recognized masterpiece of engineering. It proved a fundamental truth about uncovering history, that the most important stories are often hidden in plain sight, waiting for the right technology to listen. The ghost had a voice, and it was about to start speaking in the precise language of mathematics and celestial motion. The radiographs provided the blueprint, but the true genius of the machine lay in what those gears were designed to calculate. Scholars now understood they were not looking at a clock, but at a cosmic oracle. The Antikythera mechanism was a precision-engineered model of the heavens, a portable planetarium powered by a simple hand crank. By turning a small input handle on its side, an ancient user could advance or rewind time, watching as intricate pointers on multiple dials traced the complex dances of the sun, the moon, and the 5 planets known to the Greeks. It could show the phase of the moon on any given date, predict the next solar or lunar eclipse, and even account for the moon's subtle wobble in its orbit, a motion called anomaly. This was not magic, it was mathematics made physical. Each meticulously cut gear served a specific computational purpose. For instance, one critical gear train embodied the Metonic cycle, a period of 19 solar years that equals almost exactly 235 lunar months. This cycle was crucial for keeping lunar-based calendars in sync with the solar year, and the mechanism's gears reproduced this 19-year period with stunning accuracy. Another set of gears calculated the Saros cycle, a period of about 18 years and 11 days after which the Sun, Moon, and Earth returned to nearly the same relative geometry, meaning eclipses repeat. The machine could predict not just that an eclipse would occur, but its likely time and whether it would be solar or lunar. Perhaps most beautifully, one of its dials was inscribed with the names of Pan-Hellenic athletic games, including the Olympics. This feature connected the grand, impersonal clockwork of the cosmos directly to the rhythm of human celebration. It suggested that the same cosmic order that governed eclipses also marked the 4-year cycle of sacred competition and truce. Understanding this purpose transforms the corroded bronze from a curiosity into a profound philosophical statement. It reveals an ancient Greek world, where human life, civic events, and the motions of the heavens were all part of one interconnected, predictable system. The mechanism was a tool for navigating that system, for bringing the order of the cosmos down to human hands. To appreciate this machine, we must look at its bones, the gears themselves. The engineering is not just advanced, it is anachronistic. At its heart is a component called a differential gear. In simple terms, this is a special assembly of gears that can combine 2 rotational inputs into one output, or conversely, split one input into 2 outputs. You encounter this principle every day in the axle of a modern car, allowing the wheels to turn at different speeds when you go around a corner. That technology, in automotive form, is credited to the 19th century. Yet here it is, functioning perfectly inside a 2,000-year-old Greek device. In the Antikythera mechanism, the differential gear was used to model the moon's complex orbit, subtracting one regular motion from another to produce the moon's observed speed changes in the sky. This was not a lucky guess. It was a deliberate, mathematically informed solution to a celestial problem, miniaturized into bronze. The physical craftsmanship is equally breathtaking. Each gear tooth was not merely filed into shape, it was precisely calculated and cut. The teeth are triangular, with their angles carefully designed to mesh smoothly, minimizing friction and backlash, which is the tiny bit of slack or play between gears. Too much backlash and the pointers on the dials would wobble, introducing error into the cosmic predictions. The creators understood this. They likely used hand-powered lathes and drills, along with cutting tools tipped with hardened iron or even precious stones, to achieve a level of precision we would measure in fractions of a millimeter today. The bronze alloy itself was specially formulated, a mix of copper and tin that was hard enough to hold an edge but not so brittle it would shatter under the stress of being turned. This speaks to a deep, accumulated knowledge of metallurgy. Perhaps the most profound challenge was not cutting the gears, but designing them in the first place. Planets do not move in simple, uniform circles across our sky. From Earth's perspective, they appear to speed up, slow down, and even loop backwards in retrograde motion. The Greeks modeled these paths using geometric theories involving circles upon circles, called epicycles. Translating those abstract, mathematical theories into physical gear ratios required genius. Someone or some group had to perform the calculations. They had to decide that a gear with 127 teeth needed to mesh with a gear of 223 teeth to accurately model Venus's cycle, for example. This is applied astronomy of the highest order. It implies the existence of a workshop, a tradition where mathematicians, astronomers, and master artisans collaborated. They were not just philosophers contemplating the cosmos from a distance. They were engineers reaching out to build a working model of it. This single artifact shatters the comforting myth of linear progress. It tells us that a peak of mechanical sophistication was reached in the ancient Mediterranean, a peak that would not be scaled again in Europe for over a millennium. The knowledge required to build it, the tools, the workshops, the very mindset that such a device was possible, all of it vanished. The mechanism is a lonely survivor from a lost lineage of technology, a whisper of a path not taken. It forces us to ask a haunting question. If this one device was saved by a shipwreck, what other marvels were lost to the quiet erosion of time, leaving no trace in our history books? The silence that followed its creation is as profound as the device itself. While the gears revealed the machine's mechanical soul, its voice was etched in metal. Across the surviving plates and dials, thousands of tiny Greek characters are inscribed, each one carved with a steady hand. This is not decoration. It is a user manual and a technical specification, fused directly to the device itself. For over a century, these inscriptions were hidden under layers of corrosion, as silent as the gears they described. Modern imaging techniques finally brought them to light, and scholars like Alexander Jones have spent years painstakingly translating these fragmented texts. What they found was a detailed guide to the cosmos. The words label celestial bodies, name the 5 known planets, and explain how to read the various dials and pointers. One crucial section, known as the Eclipse inscription, is a kind of astronomical almanac. It lists predicted dates for solar and lunar eclipses, and it accompanies these predictions with brief, evocative descriptions. The text might note that an eclipse was associated with a particular wind direction, or that it carried a certain traditional meaning. This tells us the mechanism was not a cold, abstract calculator. It was a practical tool for understanding and anticipating celestial events that held deep cultural significance. Eclipses could be seen as omens, and having advanced knowledge of them would have been a source of considerable power and insight. Beyond predictions, the inscriptions anchor the device in the rich intellectual culture of its time. The terminology used aligns with the astronomical theories of the day, linking the machine directly to the works of known Greek thinkers. The very act of inscribing so much text onto the device suggests its creators intended it for more than just a single expert. It was designed to be read, studied, and operated by someone who needed guidance. This transforms our understanding of its purpose. The Antikythera mechanism was likely both a sophisticated research tool for an astronomer and a brilliant teaching instrument for a philosopher's student. By turning the handle and watching the pointers move in harmony with the inscribed text, a learner could see the abstract theories of planetary motion made physically real. It connected the dots between mathematical equations scribbled on papyrus and the actual behavior of the night sky. The inscriptions are the final piece of evidence that this was no isolated oddity. It was a product of a thriving, interconnected scientific community, one that believed the secrets of the universe could not only be understood, but could be held in your hands. The mechanism did not emerge from a vacuum. It was born in a world ablaze with intellectual curiosity, a time we now call the Hellenistic period. Following the conquests of Alexander the Great, Greek culture, language, and ideas spread from the shores of the Mediterranean all the way to the borders of India. This created a vast, interconnected world of exchange. At its heart were great centers of learning, most famously the Library of Alexandria in Egypt. Imagine a place where scholars from across the known world gathered, argued, and shared knowledge. They translated Babylonian clay tablets filled with centuries of celestial observations. They debated Egyptian engineering techniques and Persian mathematical concepts. In this vibrant melting pot, the theoretical genius of Greek geometry met the precise, data-driven astronomy of the ancient Near East. This fusion was the essential fuel for a device like the Antikythera mechanism. You needed the Greek love for elegant models of the cosmos, but you also needed the Babylonians' relentless, centuries-long record-keeping of planetary positions and eclipse cycles. The mechanism's predictive power sits directly at this intersection. It is a physical embodiment of a conversation between two great ancient civilizations. This was an era of towering minds who thought on a cosmic scale. Figures like Archimedes, who reportedly built planetariums and ingenious war machines, and Hipparchus, who discovered the precession of the equinoxes and mathematically modeled the moon's irregular motion. The ideas needed to design the Antikythera gears were circulating in the air of this era. It was a time when understanding the universe was seen as the highest form of power, both intellectual and political. Royal courts, especially the Ptolemaic dynasty in Alexandria, actively patronized scientists and engineers. Creating a masterpiece like the Antikythera mechanism served a dual purpose. For a scholar, it was the ultimate proof of a correct theory, a working model of the heavens. For a king or a wealthy patron, owning such a device was a symbol of supreme enlightenment and control. It demonstrated command not just over land and armies, but over the fundamental laws of nature themselves. So, when we look at this intricate bronze computer, we are not looking at a mysterious outlier. We are looking at a logical, if extraordinarily advanced, product of its time. It represents a peak moment where knowledge, craftsmanship, and ambition aligned perfectly. This context makes its subsequent disappearance from history all the more poignant. It shows us that such peaks are not permanent. They can be reached, marveled at, and then lost, waiting for the tides of time to wash a single fragment back to shore, so we might remember what was once possible. The identity of its maker is a mystery written in gears and mathematics, not in stone. No signature graces the bronze, no ancient text records its commission. Yet, within its precise calculations, scholars hear echoes of specific, legendary minds. The most compelling voice belongs to Hipparchus, an astronomer working on the island of Rhodes in the 2nd century before the Common Era. Hipparchus is famed for discovering the precession of the equinoxes, that slow wobble of Earth's axis that shifts the stars over millennia. More directly, he developed a complex theory to explain the moon's subtle speeding up and slowing down in its orbit, a motion called anomaly. The Antikythera mechanism's gear train for the moon is a physical, working model of Hipparchus's very calculations. It is as if someone took his mathematical papers and translated them directly into turning bronze. The shipwreck itself has been dated to around 60 or 70 years before the Common Era, placing the device's creation squarely in the era when Hipparchus's ideas were revolutionary and fresh. This powerful link suggests the mechanism could have been built by his students or followers, perhaps in a workshop on Rhodes, turning groundbreaking theory into a tangible teaching tool. But another, even more legendary name also shadows this artifact, Archimedes of Syracuse. Ancient writers like Cicero described Archimedes constructing incredible planetariums, bronze spheres that showed the motions of the sun, moon, and planets. When Roman forces sacked Syracuse in 212 before the Common Era, the general Marcus Claudius Marcellus is said to have taken only two things as personal plunder: a flawed star globe and a working planetarium made by Archimedes. The Antikythera mechanism is precisely the kind of device those ancient accounts describe. While it was found on a Roman ship sailing from Greece to Italy generations after Archimedes' death, it is possible the design itself, the intellectual blueprint, originated in his legendary workshops and was copied and refined by later generations of engineers. This debate is more than academic trivia. It places the mechanism at the exact intersection of known history and tantalizing speculation. If it is connected to Hipparchus, it is a direct product of the era's most advanced astronomy. If it carries a lineage back to Archimedes, it becomes a relic of a lost golden age of mechanics. Either way, the search for its creator is a detective story that spans centuries, reminding us that this single surviving device is a lonely representative of a whole world of sophisticated technology that has since vanished beneath the waves of time. Within the mechanism's compact cosmos, the moon is not a simple, steady companion. Its pointer on the dial does something extraordinary. It speeds up and slows down in a precise, repeating rhythm, mirroring the moon's actual, uneven journey around our planet. This is the lunar anomaly, a subtlety known to ancient astronomers but a nightmare to model with simple, uniform gears. To solve this, the Greek engineers invented a miniature mechanical masterpiece, a device modern researchers call the pin and slot mechanism. Imagine a single, central gear turning at a constant speed. Attached to its face, slightly off-center, is a small pin. This pin sits inside a curved, slot-shaped cutout on a second, overlapping gear. As the first gear turns, the pin pushes against the sides of the slot. But because the pin is off-center, its push is not constant. For part of the rotation, the pin engages the slot early, giving the second gear a little kick to speed it up. Later in the rotation, the engagement is shallower, allowing the second gear to lag slightly, slowing it down. The result is a beautifully elegant simulation of non-uniform motion, all derived from a single, steady input. This pin and slot assembly is a physical expression of a profound astronomical concept, the epicycle. Greek theorists proposed that the moon's path could be explained if it moved on a small circle, the epicycle, whose center itself traveled on a larger circle around Earth. The pin and slot is the mechanical genius that makes that abstract circle-upon-circle theory turn in real bronze. It translates a complex mathematical idea into a tangible, predictable motion you can see with your own eyes. The accuracy is staggering. By calculating the gear ratios and the placement of that pin, the creators encoded the moon's 8-year cycle of speeding up and slowing down into a handful of interconnected parts. This means an ancient user, perhaps a philosopher or a temple priest, could crank the handle and watch a pointer accurately replicate a celestial behavior that took generations of patient night sky observation to even notice. The lunar mechanism does more than tell time. It tells a story of deep cosmic understanding. It reveals that these engineers saw the universe not as a realm of perfect, unchanging circles, but as a dynamic system with its own rhythms and irregularities. They embraced that complexity and found a way to build it. In that one small assembly of gears, a pin and a slot, we see the bold leap from observing the heavens to holding a working model of their intricate dance in the palm of your hand. But the machine's ambition reached far beyond our moon. On its front face, 5 distinct pointers were dedicated to the wanderers, the planets known to the ancient Greeks. Mercury, Venus, Mars, Jupiter, and Saturn each had their own journey to trace across the device's dial. Modeling these paths was the ultimate engineering challenge, for the planets do not behave like well-behaved clockwork. From our earthly perspective, they perform a strange celestial dance. For most of the year, a planet will drift steadily eastward against the backdrop of stars. Then, for a period of weeks, it will appear to halt, reverse direction in a westward loop, pause again, and finally resume its original eastward path. This retrograde motion baffled ancient observers, seeming to defy the perfect, orderly heavens they believed in. To replicate this irregular loop on a bronze pointer, the creators of the Antikythera mechanism almost certainly employed a brilliant solution: epicyclic gearing. Think of it as a gear within a gear, A small gear called an epicycle rotates on its own axis while being carried around a larger central gear. The tip of a pointer attached to that small gear would trace a looping path, speeding up, slowing down, and even doubling back, perfectly mimicking the planet's retrograde dance in the sky. This is not a simple idea to mechanize. It requires precise calculations to determine the size of each gear and the speed of each rotation so that the pointer's loop matches the planet's actual cycle, which could be 12 years for Jupiter or 30 years for Saturn. The surviving fragments suggest the device used a complex assembly of at least 7 additional gears just to drive these planetary displays. This transforms our understanding of the machine completely. It was no longer just a calendar or an eclipse predictor. With these planetary pointers, it became a comprehensive orrery, a complete mechanical universe inside a box. By turning the hand crank, a philosopher could watch the entire known cosmos enact its grand, slow ballet. This was the geocentric model in motion, with Earth imagined at the center and everything else revolving around it in a symphony of interlocking circles. The inclusion of the planets elevates the device from a technical marvel to a profound philosophical statement. It visually demonstrated the core belief of the age, that the universe was a place of divine order and mathematical harmony. The unpredictable wanderers were not chaotic. Their apparent loops were revealed as part of a predictable, beautiful pattern. To operate this machine was to witness cosmic order made tangible, a reassurance that even the most perplexing movements in the heavens obeyed a rational, knowable law. Among its many wonders, a single spiral dial held the key to one of the most awe-inspiring events in the ancient sky. This is the Saros dial, a complex, coiled track on the back of the Antikythera mechanism dedicated solely to predicting eclipses. To the Greeks and Romans, an eclipse was far more than a celestial shadow. It was a potent omen, a moment when the predictable order of the cosmos seemed to falter. The sudden darkening of the sun or the blood-red hue of the moon could signal divine displeasure, foreshadow the fall of a king, or portend coming conflict or famine. Predicting these events was not just a scientific exercise, it was a vital form of social and political intelligence. The Saros dial made this power mechanical and repeatable. By turning the hand crank, a user could watch a pointer advance along this spiral groove, moving from one cell to the next. Each cell represented one lunar month, and the entire spiral mapped out the Saros cycle, a period of approximately 18 years and 11 days after which the Sun, Moon, and Earth returned to a nearly identical alignment. This cycle, known to Babylonian astronomers centuries earlier, meant eclipses repeat in a predictable pattern. The genius of the mechanism was to encode this vast, abstract cycle into a tangible, navigable map. The dial did more than just mark a date. Tiny inscriptions within each cell provided a short forecast. They indicated whether an eclipse would be of the sun or the moon, and they often included brief descriptors like the expected color of the event or the direction from which it would begin. This transformed the device from a simple calculator into a detailed celestial almanac. Imagine the authority this granted its operator. In a world where rulers consulted priests and oracles before major decisions, the ability to calmly announce, based on a bronze machine, that a solar eclipse would occur on a specific afternoon in 3 years' time, and that it would begin in the northwest, must have seemed like a form of divine knowledge. It democratized a secret that had once required a lifetime of studying clay tablets and memorizing complex cycles. Now, with the turn of a handle, a scholar, a ship's captain, or a civic planner could access this profound insight. The Eclipse Predictor underscores the mechanism's ultimate purpose. It was a tool for navigating uncertainty, for bringing the terrifying and the sublime within the realm of human understanding and perhaps human control. Yet the cosmos it modeled was not a cold, empty space. On the back of the device, a second spiral dial held a different kind of rhythm, one written not in the language of planets, but in the names of men and cities. This was the Olympiad dial, a unique feature among all surviving ancient artifacts. While the other dials tracked celestial cycles of months and years, this one marked a 4-year period defined entirely by human celebration, the cycle of the Panhellenic Games. As the pointer moved along its track, it would pass through small, inscribed cells naming the great athletic festivals: the Olympics at Olympia, the Pythian Games at Delphi, the Nemean Games, and the Isthmian Games. This simple, brilliant inclusion transforms our understanding of the machine's purpose. It was not merely a scientific instrument, it was a cultural compass. In the fragmented world of the Hellenistic era, where Greek-speaking cities were scattered across continents and often politically divided, these games were a powerful unifying force. Every 4 years, they enforced a sacred truce, drawing athletes, artists, and spectators from hundreds of miles to compete in the name of shared gods and shared heritage. The mechanism's designer chose to embed this social calendar directly into the cosmic clockwork. By doing so, they made a profound philosophical statement that the rhythm of human society, our festivals and our truces, was as regular and as meaningful as the orbit of the moon or the cycle of an eclipse. Turning the crank to see when the next Olympics would fall was an act that connected civic planning to celestial order. A ship's captain might use it to know when the seas would be crowded with pilgrims traveling to a festival. A city official could anticipate the need to train athletes or prepare ambassadors. It served as a practical reminder of upcoming events that defined Greek identity, but on a deeper level, it visually reinforced the idea that human time and cosmic time were woven from the same thread. The machine declared that the games were not just a local tradition, they were a feature of the universe itself, as predictable and as significant as the rising sun. This blending of science and culture shows the mechanism was never intended for a lonely scholar in a tower. It was built for a community, for a world that saw no separation between understanding the stars and celebrating what it meant to be human. In its gears, the sacred and the scientific found perfect ticking harmony. The machine's silent gears hold another secret, the story of their own creation. To build a cosmic calculator, the makers needed more than brilliant blueprints. They needed a material that could translate those dreams into durable, moving reality. Modern analysis of the fragments reveals their choice, a specific bronze alloy of roughly 95% copper and 5% tin. This was not a random mixture. This particular blend offered a perfect balance, providing enough hardness to be carved into precise, sharp gear teeth that would not quickly wear down, while retaining enough malleability to be cast into thin, complex plates without becoming brittle. They understood metal in a way that was both art and emerging science, selecting an alloy that would stand the test of time, even at the bottom of the sea. The process likely began with lost wax casting, a technique known to the ancient world but executed here with extraordinary finesse. A craftsman would first sculpt the individual gear or plate from beeswax, capturing every tooth and inscription in minute detail. This wax model would be encased in clay to form a mold, then heated so the wax melted and drained away, leaving a hollow cavity in the exact shape of the part. Molten bronze heated in a clay crucible over a charcoal furnace would then be poured into this cavity. Once cooled, the clay mold was broken away, revealing a rough bronze casting. But this was only the beginning. The real magic happened in the finishing. Each gear, likely no thicker than a modern coin, had to be made perfectly flat and its teeth brought to a precise, uniform profile. They would have used hand-powered lathes, perhaps turned by a bowstring, to spin the casting against hardened iron or stone files. The triangular teeth were not merely filed into shape, they were individually calibrated. The angle of each tooth slope was critical, determining how smoothly it would mesh with its neighbor and how much slack or backlash would exist in the system. Too much backlash and the pointers on the dials would wobble, introducing errors into the cosmic predictions that were the machine's entire purpose. This speaks to a workshop environment of exceptional skill and patience, where artisans, possibly working under the guidance of an astronomer-mathematician, understood the intimate relationship between material, form, and function. They were solving problems of friction, wear, and precision that would not be formally studied for centuries. The quiet hum of their lathes and the scrape of their files were the sounds of engineering being born, not from a textbook, but from the empirical need to make an idea of the heavens physically and flawlessly turn. The ship that carried this marvel was no ordinary vessel. Resting 45 meters below the surface near Antikythera, its wooden hull long dissolved, the wreckage paints a vivid picture of luxury and loss. Scattered across the seafloor, archaeologists recovered stunning bronze and marble statues, delicate glass bowls, gold jewelry, amphorae of fine wine, and even a hoard of silver coins. This was the cargo of a wealthy Roman merchant or a state-sponsored ship, a floating gallery of Greek art and luxury, goods being transported from the eastern Mediterranean to the heart of the rising Roman Republic. The coins help date the voyage to sometime between 70 and 60 years before the Common Era, a time when Roman elites were voraciously collecting Greek culture, both its artworks and its knowledge. Amidst this treasure of statues and silver, the Antikythera mechanism was packed not as a curious trinket, but as a precious piece of intellectual property. Its presence suggests a specific and fascinating journey. Many scholars believe the ship likely set sail from the island of Rhodes, a major center of astronomy and trade, and a possible home to the workshop that built the device. Its destination was almost certainly Italy, perhaps the port of Puteoli near Naples, which served Rome. Who was the intended recipient? The most compelling theory points to a powerful Roman patron, a man like Cicero or perhaps even Julius Caesar, who surrounded themselves with Greek scholars and collected instruments of philosophy and science as symbols of enlightened power. Alternatively, it could have been bound for a private library or a scholarly institution in Rome, a tool for a Greek astronomer establishing himself in the capital. This context transforms the mechanism from an isolated artifact into a moving piece in a grand historical exchange. It was a commodity of the highest order, more valuable than marble, a piece of cutting-edge technology being physically transferred from the Greek world of its creation to the Roman world of its new owners. The shipwreck captures a single, interrupted moment in this transmission of ideas. A storm, a rogue wave, or a navigational error sent the vessel, its crew, and its priceless cargo to the bottom. For 2,000 years, the mechanism lay silent among broken statues, its gears locked, its purpose forgotten, waiting for a different age to recognize the true treasure among the ruins. This single shipwreck preserved a technological ghost, but its true haunting lies in the silence that followed. The Antikythera mechanism is utterly alone. No other device remotely like it has ever been found from the ancient world, and the sophisticated engineering principles it embodies seem to vanish from the historical record for well over 1,000 years. This gap is the deepest mystery of all. How could knowledge this advanced simply disappear? The answer is not a single event, but a slow unraveling of the world that created it. The great Hellenistic centers of learning, like the legendary Library of Alexandria, faced periods of conflict and decline. These were not just repositories of scrolls, they were the collaborative engines of innovation, the workshops where mathematicians and artisans worked side by side. As political stability wavered and patronage shifted, these fragile networks of specialized knowledge began to fracture. The intricate craft of building geared astronomical computers was not written down in a manual that could be easily copied. It lived in the hands of a few master craftsmen and the minds of a small circle of scholars. When those workshops closed, that living knowledge evaporated, Furthermore, the intellectual priorities of the succeeding Roman Empire were often more practical. They admired Greek science and philosophy, but their monumental engineering triumphs were in aqueducts, roads, and architecture, not in miniaturized bronze planetariums. The mechanism was a masterpiece of pure cosmic inquiry, a luxury item for deep understanding. In a changing world, the demand for such complex and expensive instruments may have simply faded away. Then consider the objects themselves, incredibly rare and fragile. Made of valuable bronze, many may have been melted down for their metal in times of scarcity. Others, left untended, succumbed to corrosion. The Antikythera device only survived because it was sealed in a shipwreck, protected from the recycling of centuries. This collective loss forces a humbling realization. Technological progress is not a straight, inevitable line upward. It is a fragile tapestry, vulnerable to the pressures of its time. A peak of understanding can be reached, marveled at, and then forgotten, leaving future generations to reinvent the wheel, or in this case, the differential gear, all over again. The mechanism's lonely existence challenges our modern assumption of constant advancement. It whispers that our own knowledge, no matter how sophisticated, is not permanently secure. It must be maintained, taught, valued, and passed on, or it too can slip beneath the waves, leaving only a corroded fragment for some future age to puzzle over. The radiographic images were a revelation, but they were still just a ghostly blueprint. To truly understand the ancient computer, someone had to build it again. This challenge has captivated scientists, engineers, and historians for decades, leading to a series of remarkable modern reconstructions. Each attempt to recreate the Antikythera mechanism is a dialogue across 2 millennia, a conversation between ancient ingenuity and modern understanding. One of the most significant efforts was led by Michael Wright, a former curator at London's Science Museum. Working for years, often with painstaking handmade tools, Wright built a physical model based directly on the radiographic scans. His process was an act of reverse engineering, a detective story told in bronze and brass. He had to deduce not only which gear meshed with which, but also the exact number of teeth on missing components, filling in the blanks with logical deductions from the known cycles of the cosmos. His working model, cranked by hand, brought the silent gears to life with a soft, metallic whir, proving conclusively that the design was not just a beautiful theory, but a fully functional machine. A more recent and comprehensive project, the International Antikythera Mechanism Research Project, used even more advanced 3-dimensional X-ray tomography to peer deeper into the corroded layers. This technology allowed them to read inscriptions that had been invisible for centuries and to map the gear assemblies with unprecedented precision. With this data, they created a stunningly accurate digital model and later physical reconstructions. These modern builds revealed the mechanism's astonishing accuracy, but also its subtle limitations. The gear trains for the moon and the sun are incredibly precise, matching the astronomical knowledge of the time. However, the planetary models, while brilliantly conceived, would have accumulated small errors over time, a reminder that even this masterpiece was a product of its era's understanding. The process of building these replicas has been as enlightening as the finished product. Engineers discovered that certain gear ratios, like the 127 to 223 tooth pairing for Venus, produce a mathematically beautiful approximation of the planet's cycle, showcasing the Greek love for elegant numerical harmony. They also grappled with the physical challenges the original makers faced: how to minimize friction, how to align axles perfectly, and how to ensure the hand-cranked input produced smooth, reliable motion across all the dials. Each reconstruction is more than a museum display. It is a powerful educational bridge. Watching a modern model turn, seeing the pointers advance and the eclipse predictions align, makes the abstract genius of the ancient world suddenly, wonderfully tangible. It transforms the mechanism from a mysterious artifact behind glass into a living testament to a shared human drive to model the universe, proving that the distance between their world and ours is measured not in years, but in the continuous turning of a single, brilliant idea. The surface of the bronze has now been peeled back, layer by digital layer. Today, the most profound discoveries about the mechanism come not from shovels or diving bells, but from beams of light 1,000 times thinner than a human hair. Advanced three-dimensional X-ray tomography, a technology that maps objects in slices finer than a sheet of paper, is allowing researchers to perform a kind of virtual archaeology. They can digitally excavate the fused mass, separating centuries of corrosion from the original metal, and reading inscriptions that have been chemically bonded to the crust for 2 millennia. This non-invasive autopsy has yielded stunning results. The international research team has recovered over 3,500 characters of text, doubling the amount of readable manual. These new passages are not just labels, they are detailed descriptions. One recently deciphered section explains, in plain Greek, how the planetary displays should appear, confirming the device was a comprehensive orrery. Other fragments discuss the colors and winds associated with eclipses, deepening our understanding of its role as a cultural interpreter of the sky. The tomography has also refined our view of the gearing with incredible precision, allowing scientists to model the exact tooth counts and interactions in software. These digital models reveal the astonishing accuracy of its algorithms. For instance, the gearing that calculates the moon's phase is so precise it would only be off by 1 day in over 270 years. Yet these same models highlight the elegant compromises its makers made. The planetary cycles, while brilliantly conceived using epicyclic gearing, are simplified approximations. This was not a flaw, but a choice, a balance between mechanical complexity and practical utility, showing us the engineers were as much artists as scientists. The digital frontier has turned the mechanism into a living puzzle. Current debates are wonderfully specific. Scholars now argue over whether it originally had 37 gears or perhaps as many as 70. They scrutinize the faintest markings on the front plate, searching for evidence of how the 5 planetary pointers were arranged. Did they move on separate dials, or were they all mounted on a single, grand display that simulated the cosmos in motion? Each new scan offers a fresh clue. This technology also fuels a tantalizing search for connections beyond the wreck. Ancient texts mention similar devices. Cicero wrote of a bronze sphere built by Archimedes that replicated the heavens, and later Roman authors referenced planetariums owned by emperors. The digital model of the Antikythera mechanism gives us a tangible reference for what those lost marvels might have looked like and how they could have functioned. It suggests we are not looking at a one-off miracle, but at the sole surviving example of a genre, a peak of a technological tradition that once had its own masters and textbooks. Every pixel of data from these scans is a whisper from the workshop, bringing us closer than ever to the minds who dared to build a universe inside a box. The research continues, not to close the book on this ancient computer, but to ensure its story keeps turning, revealing new wonders with every revolution of the modern world's own gears of discovery. The bronze gears of the Antikythera mechanism were not an isolated miracle. To truly grasp its significance, we must see it not as a lonely star, but as the brightest point in a whole constellation of ancient ingenuity. Across the Hellenistic world, inventors were pushing the boundaries of mechanics, creating wonders that blurred the line between science, art, and spectacle. Take the legendary workshops of Alexandria. There, a brilliant engineer named Hero described and built entire automated theaters, powered by nothing more than falling weights, intricate systems of ropes, and rotating drums studded with pins. these devices could enact entire mythological plays. Doors would swing open on their own, small figures would move across a stage, and sound effects would play, all without a human hand touching the scene once the performance began. These were not just toys, they were profound demonstrations of mechanical principles, proving that complex sequences of events could be pre-programmed into a physical system. Similarly, monumental water clocks or clepsydry from this period were far more than simple timers. They incorporated moving figurines, ringing bells, and even displays that showed the passing zodiac signs, turning the measurement of hours into a public spectacle of celestial observation. The most famous mind linked to this tradition is Archimedes himself. While his bronze celestial sphere did not survive, ancient writers described it in awe. Cicero reported that it showed the motions of the sun, moon, and planets with such accuracy that it could predict solar and lunar eclipses, a description that sounds remarkably like a predecessor to our mechanism from Antikythera. These parallels are crucial. They tell us that the intellectual climate of the time was ripe for such a synthesis. The same culture that delighted in automated puppet shows also sought to automate the heavens. The same understanding of weights, pulleys, and gears that made a temple door seem to open by divine will was applied to modeling planetary orbits. When we place the Antikythera device alongside these other inventions, its existence becomes less shocking and more inevitable. It represents the pinnacle of a technological genre, applying the cutting-edge automata engineering of the day to the most ambitious subject possible, the cosmos itself. This context suggests a sobering reality. The mechanism is likely the only survivor of its kind, but it was probably not the only one ever built. Others may have graced royal libraries or philosophical schools, only to be lost to melting pots or the quiet decay of time. Recognizing it as part of a broader tradition does not diminish its brilliance. Instead, it elevates our entire understanding of the ancient world, revealing a landscape where the dream of building a working model of the universe was not just a fantasy, but a tangible goal pursued by the greatest minds of the age. This single machine shatters a comfortable myth about our ancestors. For generations, we have celebrated the ancient Greeks for their philosophy, their art, and their abstract mathematics, often viewing them as brilliant thinkers who left the messy work of engineering to others. The Antikythera mechanism proves this separation is an illusion, a modern prejudice we have projected onto the past. Here was a culture that saw no meaningful boundary between contemplating the cosmos and building a machine to replicate its motions. The same mind that could conceive of celestial spheres and geometric proofs could also design a differential gear and calculate the precise angle for a bronze tooth. This device is the ultimate rebuttal to the idea that theoretical knowledge and practical skill were distinct paths. They were two sides of the same coin, both essential to the pursuit of wisdom. The mechanism forces us to abandon a linear, simplistic view of history, where technology marches in a straight line from primitive to advanced. Instead, it reveals a landscape of innovation where brilliant peaks can rise, be admired, and then be completely forgotten, submerged by the tides of social change, conflict, or shifting priorities. This realization carries a humbling lesson for our own time. We often assume our technological mastery is permanent, the inevitable endpoint of a long climb. But the silent gears from Antikythera whisper a different story. They remind us that knowledge is fragile. The intricate craft of building such a device lived in the hands of a few masters and the minds of a small circle of scholars. When those workshops closed, that living understanding evaporated for over a millennium. It makes us wonder what other sophisticated technologies from the ancient world have vanished without a trace. Perhaps there were other mechanisms, other automata, other applications of engineering that left no shipwreck to preserve them. This artifact is a powerful call to view the past with greater humility and far more curiosity. It asks us to look at ancient achievements not as quaint stepping stones on the path to us, but as complete and sophisticated accomplishments in their own right, born from a world view where the hand, the mind, and the cosmos worked in perfect ticking harmony. The device's true power may have been realized not in a solitary study, but in a room filled with curious minds. Picture a sunlit courtyard in Rhodes or a torchlit hall in Alexandria, where a philosopher gathers his students. Instead of pointing to diagrams on a papyrus scroll, he places this bronze box on a table. A student is invited to turn the small handle. As the crank rotates, a quiet symphony of interlocking gears begins, and the pointers on the dials start their slow, deliberate dance. The instructor explains that the silver ball showing the moon's phase is now waxing, and the pointer for the sun is moving into the constellation of Leo. He asks another student to advance the mechanism by 180 turns, simulating 6 months. The group watches, captivated, as the moon's pointer completes its cycle and the sun moves to the opposite side of the zodiac. An abstract concept like the Saros eclipse cycle is no longer just a number. It becomes a journey along a spiral track that they can trace with a finger. This was learning made physical. For a student grappling with the difficult geometry of epicycles, seeing a gear train physically produce a planet's looping retrograde motion could turn confusion into a moment of crystalline understanding. The machine translated the intimidating language of advanced mathematics and observational astronomy into a visual, tactile experience. It served as a dynamic bridge between theory and observation, between the perfect circles of geometric thought and the messy, observable reality of the night sky. In a royal court, such a demonstration would have been equally powerful, showcasing a patron's command of cosmic knowledge not through conquest, but through enlightened understanding. This pedagogical genius reveals that its creators valued intuition as much as calculation. They knew that to truly grasp the cosmos, one needed to not just calculate its motions, but to see them unfold, to feel the weight of the bronze and hear the soft click of the gears advancing. In this sense, the Antikythera mechanism is a 2,000-year-old testament to a timeless educational truth that we learn deepest when we engage not just our minds, but our hands and our wonder. It was the world's first interactive planetarium, a classroom in a box that made the universe something you could hold, turn, and ultimately comprehend. Yet its influence did not end in an ancient shipwreck. The ghost from Antikythera has become a guiding star for modern minds, reshaping how we approach the puzzles of the past. The study of this single artifact gave birth to an entire scientific discipline, archaeometry, the marriage of archaeology and advanced physics. Before the mechanism, no one thought to X-ray a lump of corroded bronze from a museum drawer. That single act of curiosity, using medical technology to see inside history, established a new standard. Today, particle accelerators and three-dimensional tomography scanners are routine tools in archaeology, allowing us to read faded scrolls from Pompeii, analyze the pigments in a Renaissance painting, or map the contents of a sealed tomb without ever touching a brush. This revolution in non-invasive analysis, which lets artifacts speak without being destroyed, traces a direct line back to those first gamma-ray images of the mysterious gears. The mechanism taught us that the most profound historical secrets are often locked inside objects, waiting for the right key of technology to set them free. In the world of engineering, the device stands as a timeless benchmark of elegant design. Modern mechanical engineers and watchmakers study its gear trains with a sense of professional awe. The pin and slot mechanism for the moon's motion is celebrated not as a primitive attempt, but as a brilliantly simple solution to a complex problem, a lesson in achieving maximum function with minimal parts. It demonstrates principles of kinematic design and error reduction that are still relevant in robotics and precision instrumentation today. The very fact that a 2,000-year-old device operates on the same fundamental mechanical principles as a modern clock or a car's differential is a powerful reminder that human ingenuity, when focused on a clear problem, can arrive at timeless solutions. It humbles modern innovators, suggesting that breakthrough elegance can be found by looking backward as much as by racing forward. Perhaps its most profound cultural impact is on the history of computing itself. For decades, the narrative of the computer began with Charles Babbage's 19th-century difference engine, a room-sized behemoth of cogs and levers. The Antikythera mechanism rewrites that origin story, pushing the dawn of the analog computer back by over a millennium. It has become an iconic symbol in tech culture, a staple in lectures and documentaries, representing the deep human desire to build machines that can model reality and predict the future. It challenges the tech industry's obsession with the new by asking a fundamental question: what does it mean to be advanced? This ancient box of gears proves that advanced thinking is not defined by silicon chips or electricity, but by the creative application of logic to understand the world. It inspires computer scientists and programmers to think beyond digital binaries, to appreciate the physical computation embodied in those turning bronze wheels. Ultimately, the mechanism's greatest legacy may be as a monument to interdisciplinary collaboration. Its story could never have been unraveled by a single expert. It required archaeologists to find it, historians to contextualize it, physicists to image it, astronomers to decode its functions, and engineers to rebuild it. This collective effort mirrors the very process that likely created it, a synthesis of astronomer, mathematician, and artisan. In our modern age of increasing specialization, the mechanism stands as a powerful testament to the magic that happens when different fields converge. It reminds every researcher, inventor, and curious mind that the keys to unlocking the universe's grandest puzzles often lie at the intersections, in the spaces between established disciplines. The device from Antikythera is more than a relic. It is a call to collaboration, a whisper from the past urging us to combine our knowledge, our tools, and our wonder to build a better understanding of the cosmos, just as they did 2,000 years ago. Even with all we have learned, the mechanism still guards its deepest secrets. Decades of meticulous study have answered many questions, but each answer seems to open a new door into the unknown. The most fundamental debate begins with the very bones of the machine, its gears. How many were there originally? Current reconstructions propose around 30 to 40. But some scholars, analyzing the spacing of the surviving plates and the complexity of the tasks, argue the total could have been closer to 70. This is not just a numbers game. Each missing gear represents a lost function, a celestial calculation we have not yet rediscovered. Were there additional dials tracking the cycles of other stars or perhaps comets? The empty spaces within the corroded frame whisper of possibilities we can only guess at. Equally tantalizing is the puzzle of its front display. We know the back housed the spiral dials for Eclipses and the Olympic Games, but the front face, largely lost, was the main event. It almost certainly featured a grand, moving model of the cosmos with rings for the zodiac and the Egyptian calendar. But how were the 5 planetary pointers arranged? Some researchers believe each planet had its own small dial, like separate instruments on a dashboard. Others champion a more spectacular vision, a single, unified display where all the pointers moved together on one large plate, creating a breathtaking miniature orrery that showed the entire known solar system in synchronized motion. The difference is profound, one a utilitarian tool, the other a philosophical masterpiece designed to inspire awe. Without that front plate, we are reconstructing a symphony from a few scattered notes. Then there are the human ghosts, the maker and the owner. We hear echoes of Hipparchus in its mathematics and legends of Archimedes in its ambition. but no signature confirms their hand. Was it the product of a single genius or a collaborative workshop tradition passed down through generations? And who was it built for? The lavish shipwreck suggests a wealthy, powerful recipient, perhaps a Roman general like Marcus Claudius Marcellus the Younger, known for his love of Greek learning, or even a young Julius Caesar, whose political rise was famously linked to celestial omens. The mechanism would have been the ultimate status symbol, proving its owner commanded not just armies but the very laws of the heavens, yet their names are lost to the sea. This leads to the most haunting speculation of all: was it unique? The sheer sophistication of the device makes it hard to believe it was a one-off prototype. More likely, it was the pinnacle of a technological genre. Ancient texts mention other planetariums and celestial machines in the possession of kings and philosophers. Could there have been a small series of these mechanisms, each customized for a different patron or city? If so, their fate is a sobering lesson. Made of valuable bronze, they would have been prime targets for melting down in times of war or economic hardship. The Antikythera device survived only because it was protected by a shipwreck and 2,000 years of silt. This possibility means our understanding of ancient technology is built on a single, miraculous survivor, a fragment of a much larger lost world. These unanswered questions are not failures of research, they are its engine. Every new scanning technology, every fresh look at the inscriptions, is driven by the hope of solving one more piece of this ancient puzzle. The mechanism's enduring power lies in this perfect balance between what it has revealed and what it still withholds. It remains a conversation across time, a dialogue where we ask questions with particle accelerators and three-dimensional imaging, and listen for replies etched in 2,000-year-old bronze. Each mystery is an open invitation, ensuring that this ancient computer will continue to challenge and fascinate us, turning not just with the cycles of the moon, but with the endless human cycle of curiosity and discovery. Its rise from obscurity mirrors our own growing fascination with forgotten genius. For decades after its discovery, the mechanism remained a footnote, a curious anomaly discussed only in specialized academic papers. Its transformation into a modern icon began in earnest with those first published radiographs, images that captured the public imagination as powerfully as they did the scientific community. Here was visual proof, etched in ghostly X-ray shadows, of a technology that should not exist. This compelling contradiction made it irresistible. Soon, the Antikythera mechanism began appearing in major documentary series, its intricate gears animated to spin once more, bringing the ancient computer to life for millions of viewers. It became a central character in best-selling books exploring the history of science, often serving as the opening chapter in a new narrative that challenged the myth of linear progress. The device even inspired fictional tales, appearing in novels and television shows as a symbol of arcane, lost knowledge, a relic from a more enlightened age. This cultural journey reflects a profound shift in how we view antiquity. We no longer see the past as merely a precursor to our own time, but as a landscape dotted with its own peaks of achievement, some of which we are still struggling to comprehend. The mechanism's distinctive image, a fragment of layered gears, now adorns the covers of scientific journals and greets visitors in museums from Athens to New York. It has become a universal shorthand for ancient innovation, a bridge connecting the intellectual ambition of the Hellenistic world directly to our own technological age. Its legacy is not locked in bronze, but in the questions it forces us to ask. It champions the value of preserving even the most unassuming artifact, for you never know what secrets a corroded lump may hold. It argues for interdisciplinary study, proving that the deepest mysteries require historians, physicists, and engineers to work in concert. Most of all, the Antikythera mechanism story is a powerful testament to the resilience of ideas. A single, salvaged device can dismantle long-held assumptions and rewrite chapters of human history, reminding us that our understanding of achievement is always a work in progress, waiting for the next tide to wash in a new piece of the puzzle. That corroded bronze box, then, is a mirror. It reflects back to us not just the ingenuity of the past, but fundamental truths about our own relationship with innovation. The most startling lesson is that technological progress is not a straight, inevitable line from primitive to advanced. Human history is not a steady climb up a mountain. It is a vast landscape of rolling hills, with isolated peaks rising to breathtaking heights, only to be forgotten before the next civilization finds the path again. The Antikythera mechanism represents one such peak, a summit of mechanical and astronomical artistry that would not be reached in Europe for over 1,000 years. Its existence shatters the comforting myth of linear advancement and replaces it with a more honest and more humbling reality, a tapestry of brilliant flashes, long plateaus, and profound valleys of forgetting. This forces us to ask what other peaks from antiquity have been completely erased from our memory, leaving no shipwreck to testify to their existence. Our entire narrative of invention is built on the fragments that survived, and we must now acknowledge how much of the picture is missing. This leads directly to the second, sobering lesson: the profound fragility of knowledge. The sophisticated understanding required to design and build such a device did not live in a single book. It was a living tradition woven through the minds of astronomers, the hands of master metalworkers, and the collaborative spirit of places like Alexandria. When those workshops closed, when political stability fractured and patronage shifted, that intricate web of specialized skill unraveled. The knowledge did not slowly fade. It could vanish within a generation, becoming as inaccessible as if it had never existed. This is a powerful cautionary tale for our own digital age, where we assume our accumulated wisdom is permanently secure in the cloud. The mechanism reminds us that all knowledge, no matter how advanced, is contingent. It requires active maintenance, deliberate teaching, and a culture that values it, or it too can slip silently beneath the waves. Yet within that fragility lies its most inspiring message: the transcendent power of interdisciplinary thinking. The mechanism was not created by an astronomer working alone, nor by an artisan simply following orders. It was born at the thrilling intersection of fields, a fusion of abstract celestial mathematics with the gritty, practical genius of precision engineering. The theoretical models of Hipparchus met the metallurgical expertise of a bronze caster, and together they created something neither could have achieved alone. This collaborative magic is the true engine behind humanity's greatest leaps. It is the same spirit that drives modern ventures, where biologists work with computer scientists or artists collaborate with engineers. The device stands as a 2,000-year-old prototype for the modern research lab, proving that the most complex puzzles are solved not in isolated silos, but in the vibrant, messy spaces where different disciplines converge and spark. Ultimately, the Antikythera mechanism redefines what it means to be advanced. Its sophistication is not measured in processing speed or silicon, but in the elegant application of logic to a fundamental human desire to understand and predict the cosmos. It challenges our modern obsession with the new by asking us to look deeper into the old, to search for hidden layers of sophistication in artifacts we might otherwise dismiss. This ancient computer encourages a posture of humility and curiosity toward history. It asks us to view our ancestors not as simpler versions of ourselves, but as complete intellectual equals who approach the universe with different tools, but with the same fierce curiosity. Their quest to decode the heavens in bronze is a mirror of our own quest to model reality in code. In the quiet turning of its gears, we hear a timeless echo, the enduring human drive to build a working model of the world, to hold a piece of the universe in our hands, and in doing so, to find our place within it. That corroded lump of bronze is a breathtaking testament to a forgotten peak of ingenuity. It is a map of the heavens, a calendar for human celebration, and a mechanical computer, all contained within a box meant to be held in two hands. Our journey began with sponge divers stumbling upon a ghost in the deep, and it led us through decades of scholarly dismissal, into the revealing light of X-rays, and finally to the quiet hum of modern reconstructions. We have seen how its gears calculated lunar cycles and predicted eclipses, how its inscriptions served as a user manual for the cosmos, and how its very existence forces us to redraw the timeline of human innovation. This device does more than tell us about the past. It questions our assumptions about progress itself. It whispers that the path of knowledge is not a straight line, but a landscape where brilliant summits can be reached, admired, and then lost to the fog of time, waiting for a future age to find the trail once more. The story of the Antikythera mechanism is a powerful reminder that history is never fully written, that our understanding is always a draft awaiting new evidence. It challenges us to look at every ancient artifact, every weathered stone and scrap of metal, with a renewed sense of wonder and possibility. What other silent masterpieces are sitting in museum drawers or lying on ocean floors, holding secrets that could reshape our story? Let this ancient wonder inspire you to look deeper, to question the familiar narrative, and to remember that the boundaries of human achievement are far wider than we often assume. What lost marvels do you think might still be waiting for their moment of rediscovery? Share your thoughts below, and if you enjoyed this journey into the mysteries of history, subscribe for more explorations into the hidden corners of our past.